said, the first day we did this, we did pressure and density. Backwards, density and pressure. Second day we did this, we did pressure at various depths. We also talked about hydraulics. If you do the reading, hopefully you have done, it comments in the reading, like I said, that we are kind of ignoring a little bit of the different pressures at depths. Why is pressure different at a depth? Why does pressure increase as the depth goes down? What's that? Because the weight of the water stacked on top of it. So you can kind of get a general sense of hydraulics and what you would want to do simply based on that. Obviously, that means if you want more force on the backside of that, pushing up your car, you would just make sure that the water in the tube ideally is higher than that thing so that you can use the weight of that water, although it's not that much that would cause in hydraulics specifically. All right, there are a few terms, like I said, that I'm noticing through emails, people struggling through, so I wanted to talk about them very, very briefly. Number one, specific gravity. Let's see how well we've done on this. What is specific gravity?
Dimensionless value. A dimensionless value. It's like 3.0. It's like if you have.
It is a dimensionless value, but that's not what it is. What is it?
It's a ratio.
Ratio of what two things?
Density to water.
Yeah, it's a density. It's an unknown material to water, and the reason why you can look at a density, you'll actually see this a little bit today. What do you know about density in relation to water? Let's say that differently. Okay, ask the question differently. If a density of an object is greater than water's, it sinks. Right, absolutely. And vice versa of that. Obviously, if it is lower than that of water's, as you will also see today, then it floats. So using that as a gauge, you can get a really quick sense, essentially, of what the numeric value is. So if I say specific gravity, it is literally the density of the object to the density of water. And don't forget, hopefully this is one that you probably have close to memorized. You don't have to memorize it, but you use it so often, I think that you probably should. What is the density of water? 1,000 what? I say that, yes, that is kilograms per meters cubed, but again, we talked about meters cubed as a wonky thing, so when you think of it in a lab, what is the density of water? What measurements are we probably going to use instead? Milliliters or centimeters cubed, and units for mass, when we talk about centimeters cubed, are probably going to be grams. And the reason I suggest that is actually the straight up freaking definition of density and mass at the same time. And the answer is 1. It is 1. 1 gram equals 1 centimeter cubed or 1 milliliter. Like I said, if you go back and you measure 80 milliliters of water, that means you absolutely have 80 grams of water in that particular case. So there's specific gravity. You don't have to necessarily have an equation. You just got to know that means, obviously, if my specific gravity is 2, then my density is 2,000 kilograms meters squared. Or if it's like in the problem 1.02, then it's 1,020 kilograms per meter squared. So there's one term. The second term you're going to see in just a second, and it is gauge pressure versus absolute pressure. Now, I'll show you the math on this. I'll show you the equations with this, but this is way easier to figure out, honestly, conceptually, knowing what these things are. Okay, here's absolute pressure. Oops, yeah, no, that's right. Absolute pressure says what is the pressure inside the thing, except think about like this. You deal with pressure potentially if you need to inflate your tires, yes? Okay, you don't know, standard tires are somewhere between about 32 pounds per square inch and 36 pounds per square inch. Typically, I think closer to 30. I don't want to tell you wrong right now. I'm happy to fill up your tires for it. Most tires. Yeah. What's that? I think 36 sounds about right. Tire pressure standard. I think 36 might be right. Yeah. Okay. I said this, and then once again, it comes down to. It's between 30 and 35. Actually, I should say it is 30 and 35 for small cars, sedans, 35 and 40. For medium cars, SUVs, and trucks are supposed to be, large cars and trucks, like 40, 45. So it kind of depends on your tires, and there's going to be a rating on there. That's in PSI. Now let me ask you a question. Do you think that that is the exact, let's say this differently, what would your tire gauge say if your tires weren't filled up? Well, like you take the thing, you know the thing I'm talking about, you put on the tires, okay, to measure how much pressure is coming out of it. What is that going to say if your tires are not filled up at all? You got flat. It's going to say 0. Does that mean there's absolutely no pressure inside those tires? No. What is the pressure actually inside those tires right then? You got this. No. So? If it's 15, you got the idea. Okay, so good. You got the idea though. Yes. So what? Just say the words instead of the number. I'm not listening. What is the pressure then inside the tire? Atmospheric. Right. Except, does the tire really care about adding atmospheric to the situation? No. So basically it's this. The absolute pressure inside the tire is, well, atmospheric is 15. The gauge, the extra that we put in is, I'm going to say for sake of math right now, I'm going to use 35, even though 36, whatever. Okay, so 35. So what's the absolute pressure inside there? 50. But when you deal with tires, do you really care about that extra 15? So you do gauge. So here's the math. It's really simple. The math is just that this is atmospheric. This is the extra. AKA the extra is what it would say on the gauge. Right. Or if you want to redo the math, here it is. The extra, the change in pressure, is the pressure here minus P0, which you'll notice all I'm doing on this equation is moving this to the left side. So what's my equation for gauge pressure? Just that guy right there. So I'm thinking specifically, if you've done it yet, if there's a blood pressure, not blood pressure, pressure of like the bag, what's it called? I'm struggling. IV, yeah, the IV bag, and you'll notice, of course, they use just gravity with an IV bag in order to get the extra pressure to push in. In that particular case, the problem tells you, it straight up says what gauge pressure is. The fact that it says gauge pressure means, hey, you know it's that equation right there. Does that make sense? Yeah. All right, that being said then, let's practice real quick with that and start today. Here we go. Slideshow, current slide. Go ahead and calculate this. Calculate the absolute and gauge pressure of water at 8 meters. Then number 2 says calculate the density of the object on Spainhour's desk. I usually pick a random object. We kind of went over something, so we're losing a little bit of time, so I'll make it a little bit easier. Here's the object, and you may ask me any measurements necessary when you get there. In order, whatever. Let me know when you're ready. Play music, which will totally get me banned on or flagged on YouTube. Who cares? Yes, I'm not making money yet. Do it. Oh, you're gonna get straight. I'm gonna get straight, yeah. Okay. Now the real problem is, will YouTube block out the sound? In which case, what's up?
Oh, wait, are we doing 2 also?
Yeah, we'll do the whole thing.
Okay. Measurement.
Measurements, what do you mean? You can ask me for the measurements. I'm not telling you guys to ask me for the measurements. Shut up. Should have been more red.
5 foot swing.
7.5 centimeters.
Lift.
8.1.
8.1.
Just a heads up, when it comes to volume, base width height are very arbitrary spots. Okay, sometimes it's more easy to use than others. So do keep in mind that it really doesn't matter those names. So what might be easier is to consider it length in the X, length in the Y, and length in the Z. As long as you're doing that, just make sure you're getting different ones. So you asked me for height and width. Yeah. In that particular case, but
Oh, the Z, yeah.
yeah, let's see. 4.8. 4.8. Also, just a heads up on number 2, I did not ask. Real quick, I did not tell you what I wanted the units to be. So it's easy. In either case, I didn't tell you, but I would certainly suggest it. What other measurement do you need? Got enough to get volume. That. Yeah. I'm not gonna be that nice, but I will tell you this is 5. That is the information. Alright. Was that not? That's all you need. Yeah, help me out. I didn't write it down. What were they again?
7.5 centimeters height, 8 width, 8.1.
So 7.5, 7.5, 8.1, and 4.8, right?
Yeah.
I wrote it on the board, although that's not going to help people online. I'm getting people online, by the way. I'm not just ignoring you. I mean, let's be honest. Are you people online actually doing the problem like you should? I hope so, but...
I think so.
Did you guys do a 1 okay, or do you want me to do it? Actually, I'll just do it, and you guys can tell me if you need it. All right. So if I want to find absolute engage, again, it's this equation right here. Oops. Nope. And again, the reminder is when you're looking at this, here's how you want to look at it. That is always what? Based on what we said, which pressure is that one? That's absolute, right? Then you take the difference off of this, so that means that is gauge right there. So if I'm asked both, usually what I end up doing is just calculating this one first, and then adding the initial. So that would be, this guy would be 1,000 kilograms meters cubed times G times 8 meters, and I believe that's 78,000 and change.
Yes, it is.
78,400. What are the units on that? That's pascals. Yep. Just a gentle reminder: pascals is what set of units? Nope. A pascal is what is pressure in general? You said, what is it?
Newton meters squared.
Newtons per meter squared is correct, yes. So this right here is the gauge. That's just that piece. So to get absolute, all I have to remember is what's atmospheric in pascals? Oh, you're going to do the times 10 to the fifth? It's totally up to you, whatever you find more comfortable. I think when doing something like this, it might be easier just to see the numbers written out, but both are completely fine. So it should be like what, 179,700 pascals? There you go.
Oh. Okay.
It's all right, that's kind of confusing. This part right here, that's your gauge.
Yeah, that's what I had.
And this one is your absolute.
Got it.
Good night, the writing is terrible. All right, density of the object, do you have it? Let's keep right now. By the way, just a reminder, if I tell you pounds, that is what you measurement? He says as he writes it on the board. Pounds is a measurement of weight, yes? What do you got to go to first? Newtons. So 1 pound is 4.45 newtons. So that's 22.25 newtons. And of course, Fg equals mg. So m is equal to Fg divided by g, or 22.25 newtons divided by that 9.8. So let's go 2.27 kilograms. So your density is going to end up being mass over volume. So that's, let's do this. Let's do 2,270 grams. If you left it in kilograms, that's fine, but it's going to be easier to go to grams than it will be probably to convert all your centimeters to meters. Totally your call. If you would prefer the other way, that's fine. Okay, and then divide by simply, let's go, what is it, 7.5 centimeters times 8 point, what did I say, 6? Is that, no, it's 0.1. Can't read my own writing. 4.8 centimeters. So you should have times 1,000 divided by 7.5 times 8.1 times 4.8. I have 7.79 grams per centimeter cubed. Of course, if you went to kilograms per meters cubed, that's completely fine. As we discussed before, we've already talked about that conversion. It's just 1 to 1,000. So your answer, if you'd gone kilograms per meters cubed, should have been 7,790, or maybe something a little bit off of that because of rounding. Fist to 5, your ability to do these problems.
I got it right.
Cool beans. Cool beans. Cool beans. All right. If you have questions, once again, I want to reiterate, email. I am trying a new thing that I've helped out a handful of people with, and that is when you take pictures of your work and sending that to me, I am now trying to use an iPad to draw directly on your work and send you that picture back. So I can just be like, hey, see this positive right here? Should have been a negative, and the rest of that is just fine. Hopefully that making it much more... I am in a bad habit, I feel like, right now. If you ask me questions and I show you how I do it, which is not necessarily helpful to you because you're not the one doing the active work. So I want to do a better job of engaging with your work and not with me just doing the problem. So, like this. All right, moving on. Okay, pressure at the, this one should go much quicker. Okay. Pressure at the bottom of the glass filled with water, density of which, of course, is your standard water density, is P. Water is poured out and the glass is filled with ethyl alcohol with a lower density. The pressure at the bottom of the glass is now what? What's that? Y should be smaller than P. I agree with you, but that is the right answer. Y. But what is that? Why should it be?
Less density, so it's on top of it.
So, and the other thing is less density, but you want to add to that, correct? But you'll notice that in this case, it's entirely filled with water and then entirely filled with ethyl alcohol. A smaller density means there's a less amount, with the same amount of volume means less mass, which less mass in turns means less force of weight. Yes, there's less force of gravity. There's less weight on top of it, and therefore, yes, the pressure should be smaller. Several common barometers are used in a variety of fluids. Which fluid will the column of fluid in the barometer be the highest? So barometers, if you'll remember yesterday, was this guy, okay? Right? So assume that this liquid right here is all of those different elements. Too far. Oh, too far. There we go. Which fluid will it be the highest? By the way, just a reminder, I think I said this before, but just when you look at this, it doesn't say it on here. That left side over there are all solids. This right side over here is where you get to the fluids, liquids, and gases. So when you're looking at something that is obviously filling it up, it's probably going to be gas. So obviously you got your benzene right there. What's the answer? Which one should be the highest? No. Should be ethyl alcohol.
Yes.
Why should ethyl alcohol be the highest in that case? So it's least density, so it's kind of the opposite of the last situation. In order to get the same amount of pressure, you're going to need more weight. So you need more weight with a smaller density means a larger volume. So that's why I kind of stopped you a little bit on just saying, hey, smaller number, smaller. You got to be wary, because in this case, smaller number actually means a bigger number because of looking at volume versus output. All right. All right. Blood pressure is normally measured on the cuff with the meter around the arm. Suppose that blood pressure is measured with a cuff around the calf of the leg of a standing person. What will the blood pressure reading be? So instead of putting the cuff around your arm, you put the cuff around the calf. What should happen to the blood pressure reading? Same, less, greater? Absolutely greater, yes. You do not have the same blood pressure every single spot in your body. Why is the blood pressure in your legs obviously got to be bigger? Because, yeah, and then the reason why, of course, is because you got gravity that it's fighting against, and so it has to be pushed harder into your legs, of course, in order to get out. Okay. All right. Conversation today is, I'm going to say quick, but then I don't want to go too hard. Yeah, it's relatively quick, but it's a lot of something a little bit of the repeat. All right. So this is somewhat of a repeat of a conversation, but kind of in a different perspective in what we're looking at. Okay, the arrows that you see representing in this case, you will notice a very important distinction between this picture right here and the next one. Okay, now it's very, very subtle, obviously, the shade on that circle, but I want to talk about the shade on that circle first. Okay, this means, hey, let's not think about any object in this water whatsoever. Let's just imagine a circle, a sphere of water that we are looking at. These arrows represent the force. And what force is acting on that bubble? What's causing that? What's that picture in your head? Collisions, right. And as we discussed from the equation last time, there should obviously be more collisions on the bottom than there should be on the top. And if we took all of these arrows and added them all in a vector addition, what would we find about the horizontal components probably? They're gonna equal and opposite, so they're gonna cancel each other out, even though those are going in different directions. Now, here's what I want you to think of. There is water here, okay? Because there is, not anymore, there's not. There is water here. And because of that, you can see the pressure on the bottom, the force on the bottom has to be greater than the force on top. But we don't assume that that water is probably moving anywhere. So what's probably true about those forces? They have to be equal. Okay, what are those two forces that are equal? Force of gravity. So it'd be the force of gravity of the water itself, and let's just call this force of water, right? This force of water is really a difference between the forces going up and the forces going down, but we know the forces going up on the bottom are always going to be greater. There's always going to be a force up. And in this case, we know they have to be equal because we don't expect the water to be going anywhere. Again, Drawing an imagination, there's collisions on top, there's more collisions on bottom. Those more collisions on bottom essentially make it that that water is being held in place. Yes? Okay. So now, instead of that body of water, I take a actual physical ball and I put it in that spot. Okay? So now the water is no longer there. Yes? But does the surrounding water have any idea that the water is not there? No. So is it still pressing up the exact same way it did just a moment ago? Yes, it should be exactly. I don't know why I'm shaking my head the way I'm. This should be exactly the same. Again, the water pressing up is causing those collisions underneath versus on top, and it is holding that water in place, right? There's collisions on top, collisions on bottom, keeping that in place. And I put a ball into that spot. The water, non-sentient object, does it have any idea that the water that was here is no longer here? It has no idea. So is it still causing the exact same amount of collisions below and above? Yes. So this force is the difference between those two. As a matter of fact, you'll see it in just a second. It's just this. It is the difference between those pressures. We saw it on the previous slide. But we know it is, watch this carefully, this force, I'm going to give it a name. We're going to call this the buoyant force. Okay? And based on the previous slide, watch this, we know that that force has to be equal to this gravity, specifically the gravity of this liquid, right? So even though that liquid's not there anymore, I know that the buoyant force is equal to the gravity of the water that it displaced. How are we doing now? So not the gravity of this guy. It doesn't know. But there's water that's gone from this spot that had weight. And that weight was perfectly balanced by the collisions on the outside of that. Yes? And now the water's not there, but those collisions still are. They're colliding an equal amount as they would have if the water still had been there. So that means buoyant force is equal to the gravity of the displaced fluid. So here it says mg, where m is the mass of the displaced fluid. Now, what's up?
So is this like if you put it in there, or is this like if it appears in there? Like just
put it straight in.
Just put it straight in.
Put it straight in, absolutely.
Out.
Yeah, I'll show an example on Monday. Actually, I've got a few demos that I want to show you in person, and I'll just take objects and just drop them into the water. But again, the water doesn't know. And actually, in this particular case, the depth doesn't matter. And the reason the depth doesn't matter is this. If I take, say, a rock, right, and I drop it in the lake, right? So a relatively, let's not do a rock. Let's just do this. This volume, this 5-pound object right here. Does its volume change as it goes down? So is it displacing the same amount of fluid as it goes down? Yes. Now, does the pressure underneath get bigger as it goes down? Yes. But does the pressure on top get bigger as it goes down? Yes. And they get bigger by the same amount. So is the difference still going to be the exact same all the way down? Yes. It should be different the entire way down. Okay, so we talked about this before. Is mass easy to measure for a fluid? No. So instead, probably a better thing to do in this particular case is to use density times what? Times volume. Density times volume gets us this mass. And then if I've got the mass, all I got to do is multiply by. Now, a warning right now, and I specifically draw the first problem today in order to kind of solve this. Notice how similar this looks to gauge pressure. utterly and completely similar. Major difference, of course, being that this is in fact volume and this is not going to cancel any. This is the volume that we want. Okay, and also let's say this is the volume and density of the fluid, not of the object. All right. So we can get the same type of thing out of the previous equation. I think I mentioned this a second ago. Essentially, here's what you got. What are they going out of this? Actually, I just showed it on the previous slide. I don't like this slide. I'm gonna go away from it. All right. So let's talk about objects that sink and objects that float, and why this is. Here I've put a piece of wood in this particular thing. You'll notice that the buoyant force is pointed up. We discussed the buoyant force is equal to what? I want you to say it now. The what? It's the what?
Mass of pressure.
What is, so it's equal to the weight of? Correct, thank you. That's what I needed. Yeah, the weight of the displaced fluid. So watch here carefully. Here I have a piece of wood, and here I have a piece of metal. Should their buoyant forces be any different? Should the buoyant forces of these two guys be any different? No. Why not? Thank you. They're displacing the exact same amount of volume in both cases, so the same amount of weight of water is the same, and you can see that on the picture, that the buoyant forces are equal in both cases. Obviously, the wood is way less dense than water. You expect wood to float. So why is it then that wood floats, and why do we consider density as this thing? Well, guess what? If the density of wood is less than water, then the mass of this wood is going to be less than the mass of the water that it displaced. So the weight down is smaller than the force up. So this is basic Newton's second law. What does it do? Accelerates up. It will 100% accelerate up. And the vice versa is, what if density is greater than water? Well, if density is greater than water, the mass of this is bigger than the mass of the water that was there, which means the gravity is bigger than the force pushing up, and so this will also accelerate downward. Exactly. Now, in this particular case, you will notice a very important thing, that the volume of the object and the volume of the fluid are equal. Okay, so we got buoyancy is equal to density times volume of the object times gravity, and the weight is equal to the density of the object times volume times gravity. The only thing that's really changing here is what the density is of these materials. That's, again, why we talk about density, even though what we really care about is mass, because basically the volumes are exactly the same in both cases. So we calculate net force, and then we just get acceleration, which way it's going to go. So again, this is an important distinction for today. You'll notice the top title there. This is when they are totally submerged. Okay, so what if it's floating? If it's floating now, what changes? We don't actually worry about air pressure too much. Which volume changes? So you get two things here. We got volume of object and a volume of fluid. Which one changes and which one stays the same? The fluid should change. Correct. Because it's the displaced fluid. You definitely want to draw this picture. Watch here carefully. This, in that box, would be the volume of fluid. Now, I know I'm drawing this on the wood. Don't think of this, okay? Don't think of this as the wood. This is the volume of the fluid that has been displaced. Okay? This, the entire thing, that is the volume of the object. Now, of course, what objects do we expect to float based on the last slide? With objects with wood, yes, but less dense. So it makes sense that what's true of the forces here if it's floating? They got to be balanced, okay? So here we go. We have, once again, the buoyancy is equal to the density of the fluid times the volume of the fluid times g. Here we have the weight, density of object, volume of object times g. Unlike the previous slide, in the previous slide, volumes were equal. As we just got done discussing, volumes are definitely not equal right here. So we know that weight has to equal buoyancy because it's following which law? First. So watch this. This has just gotten out of, it's kind of quick to see. I'll write this up here, but then it's like the easiest force diagram ever, so I kind of skipped over it here. Sum of forces equals mass times acceleration, but there is no acceleration, so it's 0. Buoyancy minus force gravity equals 0, just that stuff. Therefore, buoyancy has to equal force of gravity, yes? And then off of that buoyancy is this, yes?
Yeah.
And of course, force of gravity is this, so this. Now, notice though, what nice mathematical thing happens here. Gravity cancels. We don't need to care what it is because it's equal for both objects. Then you can manipulate this so that the densities are on one side. I think in this case, I took density of fluid and moved it underneath, and density of object and moved it underneath. And you get this ratio here. Now remember, what's the relationship? Where am I at? I'm almost out of time, but I'm good. I'm close. I think I'm almost done. I think this is yeah, cool. I'm like literally on the last slide. Cool. All right. So even though the volumes are different, what's the relationship between volume, and I know it's not in the picture, so let me try to do a kind of a job of making three-dimensional shape here. Here's my three-dimensional shape, okay? What's the relationship between volume and area? We did this one the other day. Volume is equal to area times, what's that? Not pressure. I was just looking for height. Height of the fluid. Okay? And the volume of the object is the area the same for both the object and the fluid. Is the same area for this box, this guy right here, is it the same as that box of fluid that's being displaced? Yes. So there's a really cool thing that comes out of this, and it's this. Let's say this is water. What's the density of fluid then? It's the density of water. 1 gram per centimeter cubed. I can literally look at an object and very, very quickly find out what its density is, assuming that it's less than 1, simply based on how much of that is underneath the water. Okay, if, let's say this is, I don't know, it kind of looks even, but I'm not going to make it even for sake of argument here. If that's 6 centimeters, then that would be the height of fluid, right? If this was 10 centimeters, that would be the height of the object, and the areas would be identical. What does that mean? I would know that this wood has a density of 0.6. Now, one thing to be wary of on these problems on your homework is they're really going to check your understanding of volume of fluid versus volume of object. Draw a picture. Here's the most common way they're going to mess you up. They're going to give you this almost exact same situation with a relatively small amount of numbers in order for you to understand. They can say an object is sitting, or they'll do something like, hey, a 10 centimeter long object is sitting in water and 4 centimeters are sticking out the top. What's its density? Now, not paying very close attention, most people are just going to go, 4 divided by 10 is 0.4. But you will notice what they just gave you was this guy right here. Is that what you actually need in this particular case? We have to clearly identify what height of fluid is and height of object is. Of course, the solution is very simple. Okay, well, if the whole thing's 10 and that's 4, then obviously means that's 6, and my density is 0.6. Make sense? Well, beans. I think that's it. I'm pretty sure that's it for me today. Measurements, finest buoyancy. Oh yeah, by the way, yeah, okay, and this will be Monday. We're all set. That's it. I am done.